Hello. It is February 23rd, and 4 hours ago, every alert panel inside NASA's monitoring systems lit up red, and nothing about that was routine. This is not a simulation, not a forecast, and not a hypothetical scenario. As you're hearing this right now, an object we've been tracking for the past 18 months has done something no one was prepared for. The object is known as 3I Atlas, and moments ago, it experienced what scientists are calling a catastrophic disruption event. That phrase sounds technical, almost harmless, but here's what it actually means. The object didn't just crack or shed dust. It produced something new. At exactly 8:14 UTC, Deep Space Radar confirmed a separation event. A dense cloud broke away from the main body. This wasn't gas. This wasn't debris powder. This was roughly 50,000 solid fragments, each about the size of a river pebble, moving together in an unusually tight formation. Normally, when a comet breaks apart, the pieces scatter in every direction, chaotic and unpredictable, like glass shattering on concrete. That's how physics usually works. Disorder follows destruction, but that is not what happened here. Data rushed in from space-based observatories within the hour, and what it showed stopped researchers cold. These fragments weren't drifting apart. They weren't spreading into a cloud or trailing into a tail. Instead, they were clustering, organizing themselves into a narrow, ribbon-like stream. Even more unsettling was the precision. The angle of dispersion measured less than 0.02 degrees. That level of order is almost unheard of in natural breakups. Entropy doesn't behave this way. Nature doesn't usually line things up so neatly. And yet, that's exactly what the instruments were seeing. The shape alone would have raised eyebrows, but the real concern wasn't the structure, it was the path. Using the latest orbital parameters released earlier that morning, trajectory projections were run forward just 48 hours. The result was immediate and alarming. This newly formed meteor stream does not miss Earth. It intersects directly with Earth's orbital plane. For decades, planetary defense has focused on one nightmare scenario, a single massive impactor, a rock large enough to wipe out cities or worse. But physics tells us something different here. A swarm of tens of thousands of hypervelocity fragments presents a far more complex problem, especially for satellites and the upper atmosphere. That distinction matters, and agencies reacted accordingly. This event was flagged at the highest internal alert levels. Emergency protocols were activated, and as the data continued to update, one detail stood out above all others. The fragments weren't slowing down. Solar radiation pressure should have caused measurable deceleration. Instead, velocity readings showed the opposite. The objects were accelerating. That single fact overturned months of assumptions about 3I Atlas. Whatever this object is, it didn't simply pass through the solar system and move on. It left something behind, and that something is active. To understand why the scientific community shifted into what can only be described as a quiet emergency, we have to rewind the clock. Up until early this morning, 3I Atlas was unremarkable. Discovered in late 2024, it followed a hyperbolic trajectory, interesting mostly for its steep inclination. It behaved like a typical cometary body, a dirty snowball tumbling through space, shedding material slowly as it warmed. Then at 4 UTC, everything changed. The first warning didn't come from a telescope. It came from a radar antenna conducting a routine orbital refinement. Engineers expected a clean signal reflecting a single nucleus. Instead, the return came back fractured, filled with thousands of tiny echoes clustered around the main body. At first, it looked like interference, equipment noise, something mundane. But the pattern wasn't random. The signal had rhythm, structure. Within minutes, priority observations were ordered and space-based instruments were redirected. When the first images came back, they confirmed the impossible. The object hadn't merely broken apart, it had released a swarm. In science, a single observation is never enough. One dataset can mislead, two can be coincidence. You need three independent confirmations before something becomes real. And that's where the situation crossed from strange to deeply unsettling. The radar system had seen it first. The space-based imaging confirmed it. Then a third system, operating completely independently, detected the same event. A precision mapping spacecraft registered a sudden brightness spike at the exact coordinates of the swarm, a flash measuring magnitude 4.2. At nearly the same moment, a newly operational wide-field observatory in Chile cross-checked the region and confirmed the anomaly from the ground. Three different instruments, using three different methods, all reached the same conclusion within minutes. This wasn't equipment failure, it wasn't noise, the swarm was real, and the numbers didn't make sense. What scientists expected, if this were a normal breakup, was randomness. When comets fragment due to heat or tidal stress, the result follows a predictable pattern. You get a few large chunks, many medium pieces, and clouds of dust so fine they behave like smoke. The sizes spread out in a smooth curve. That's how natural fragmentation works. But that's not what the data showed. Preliminary analysis, quietly circulating among research teams, revealed something no one could explain. Nearly 90% of the 50,000 fragments were the same size, not roughly similar, practically identical. Measurements placed them between 4 and 6 centimeters in diameter, with a variance of less than 3 millimeters across the entire swarm. Pause on that for a moment. If you smash a rock with a hammer, you don't get thousands of matching pieces. You get jagged shards, powder, and irregular chunks. Nature is messy. Uniformity at this scale is not just rare. It's statistically absurd. Yet here were tens of thousands of objects, all shaped and sized like they'd been deliberately manufactured. That was anomaly number 1. Anomaly number 2 appeared shortly after. As tracking improved, analysts noticed something even stranger about the swarm's position. Normally, material shed by a comet lags behind it, forming a tail that stretches backward along its orbit. That's how meteor showers form. Earth passes through the dust left behind. This swarm wasn't trailing. It was leading. The fragments had been ejected forward, ahead of the parent object, in the direction of travel. That detail alone raised immediate red flags. For debris to be expelled forward, energy has to be added to it. Something has to push it. A crumbling body can't do that on its own unless there's an explosive jet or violent outgassing event. But infrared observations showed no massive heat spike, no thermal bloom. The object was cold. So now the picture looked like this. A cold body released 50,000 nearly identical objects, accelerated them forward, and inserted them into a precise trajectory that intersects Earth's orbit. That combination should not exist. Then came anomaly number 3, the one that shifted concern from curiosity to risk. Density. Meteor showers are something we understand well. Even during a powerful storm, you might see thousands of meteors per hour, and that's considered extraordinary. But radar cross-section measurements told a different story here. The density of this stream was calculated to be roughly 400 times greater than one of the most intense meteor storms ever recorded. Imagine standing in a hailstorm, except the hail is made of rock and metal, and each piece is moving at 42 kilometers per second. That's the environment satellites would face if this stream intersects Earth as projected. And then, just as models were being updated to account for this unprecedented density, something happened that no one was watching for. At 9 UTC, Doppler data began to shift. At first, analysts thought it was a calibration error. Doppler shifts tell us whether an object is moving toward or away from us and how fast, but the signal from the swarm wasn't behaving passively anymore. The frequency was fluctuating, not randomly, periodically. The fragments weren't just moving forward, they were oscillating. Entire clusters were vibrating together, subtly but measurably, as if responding to a shared influence. In every catalog of observational astronomy, spanning millions of years of modeled behavior, there is no precedent for a debris field doing this. Rock doesn't vibrate in unison, it doesn't hum, it doesn't move unless something acts on it. And whatever was acting on this swarm hadn't revealed itself yet, because the data coming next would challenge the most basic assumptions about what these fragments actually were. When scientists say the fragments were vibrating, they don't mean it as a metaphor. This wasn't poetic language or speculative interpretation. It was a measurable physical oscillation, recorded independently by multiple instruments. In classical mechanics, an object like a rock is simple. It has mass. It follows a trajectory. It responds to gravity. If you throw it through empty space, it travels predictably until another force acts on it. It doesn't shimmy. It doesn't pulse. It certainly doesn't synchronize with thousands of other objects. Yet that is exactly what the data showed. At 11:15 UTC, one of the most sensitive radio telescopes on the planet isolated the frequency of the oscillation. The results stopped the analysis cold. The entire swarm was vibrating at exactly 440 Hertz. Not approximately, not within a wide range. Exactly the same frequency across tens of thousands of fragments separated by hundreds of kilometers of space. Synchronization in nature is rare and fragile. Fireflies can briefly flash together. Some animals coordinate behavior, but physical objects, especially inert ones, don't lock into perfect harmony. If you drop a box of tuning forks, each rings at its own pitch and fades at its own pace. These fragments didn't fade. They started together and continued together. That alone placed this event outside any known natural process. The next question was obvious. What force could possibly cause this? Analysts tested every known interaction. Solar radiation pressure was the first suspect. The sun constantly pushes on objects with a stream of charged particles, but calculations showed the effect was negligible. For a solid object 4 centimeters wide, the solar wind is more like a gentle breeze against a speeding truck. It couldn't produce sustained oscillation at this frequency. For the effect to work, the fragments would have to be incredibly light, almost hollow, and that possibility was far more unsettling than any solid rock explanation. Hollow objects aren't pebbles, they're shells. Before anyone had time to absorb that implication, another physical law came into focus: conservation of momentum. If an object expels mass forward, it must recoil backward. That's not a theory. It's one of the most fundamental principles in physics. Rockets move because they throw exhaust behind them. If this object pushed 50,000 fragments forward, it should have slowed down. It didn't. Telemetry from the parent body showed its velocity remained unchanged to within a margin of 0.001%. The system gained energy without losing any. In a closed system, that is impossible. Energy cannot appear from nothing. Momentum cannot vanish. Unless the system isn't closed, unless there is an internal power source we cannot see. A preliminary internal memo circulated shortly after quantified the problem. The energy required to accelerate this mass of material without recoil was consistent with non-gravitational acceleration. In other words, propulsion. That word is almost never used in astrophysics. Natural objects don't propel themselves. But the math left no alternative. Individually, each anomaly could be dismissed as an extreme outlier. Together, They formed a pattern no statistician could ignore. The probability of a natural object breaking into uniform spheres was vanishingly small. The probability of those spheres oscillating at a single frequency was even smaller. The probability of both happening without momentum transfer was effectively zero. This wasn't just unlikely, it was impossible. And then, just when the physics community thought the situation couldn't escalate further, it did. At 14 UTC, the focus shifted from theoretical violation to operational concern. Tracking data was fed into collision avoidance software normally used to protect orbital infrastructure. The software failed, not due to error, but because the inputs didn't fit the equations. The fragments were not following Kepler's laws. Objects in orbit don't move in straight lines. They fall continuously around a gravitational well, speeding up and slowing down in predictable arcs. But for the past 2 hours, the swarm's path had been straightening. The curvature expected from solar gravity was flattening. The fragments were resisting the sun's pull. To put that into perspective, imagine throwing a baseball and watching it fly in a straight line, ignoring gravity halfway through its arc. That behavior requires constant force. It requires lift. It requires guidance. At 14:30 UTC, without explanation, a public radar feed went dark. Almost simultaneously, deep space antennas across 2 continents reoriented toward the swarm. They stopped transmitting and started listening. Because if you have synchronized oscillation, non-gravitational acceleration, and resistance to orbital mechanics, you are no longer observing geology. You are observing technology. And the data about to surface would force everyone watching to confront that possibility head-on. If this phenomenon were natural, it would mean physics itself was incomplete. It would imply the existence of a new force, a new interaction, something powerful enough to organize matter, inject energy, and override gravity without leaving a thermal signature. That alone would be the scientific discovery of the century. But the alternative explanation carried far heavier consequences, and that was the direction the data was now pointing. Because the next development didn't come from theory, it came from behavior. As the swarm continued its approach, analysts noticed a subtle but critical change in its motion. The fragments weren't just holding a straightened trajectory, they were actively adjusting it. The stream began to align itself with Earth's movement, compensating for orbital drift with corrections so precise they couldn't be explained by chance. This wasn't passive motion, this was navigation. Then came the moment that forced agencies to stop treating the situation as an astronomical anomaly and start treating it as a security event. At 15:15 UTC, an observatory designed to study the coldest, quietest regions of the universe detected something it was never meant to see. Its receivers were suddenly overwhelmed by a signal originating from inside the swarm itself. This wasn't reflected sunlight. This wasn't background noise. It was a coherent emission, sharp enough to saturate instruments calibrated to detect faint molecular clouds. The source was internal. What the observatory recorded was a rapid sequence of microwave bursts, each lasting just milliseconds, jumping from fragment to fragment at light speed. The pattern wasn't random. It wasn't chaotic. It had structure, timing, repetition. It looked disturbingly familiar, less like static and more like a network activating. The fragments weren't just vibrating together. They were communicating. In nature, matter doesn't exchange information this way. Rocks don't send signals. Dust doesn't encode data. Yet the modulation patterns showed deliberate design. Embedded within the signal were repeating numerical sequences, prime numbers spaced in precise intervals. This wasn't noise accidentally forming order. This was order imposed intentionally. To coordinate 50,000 independent objects across thousands of kilometers with millisecond accuracy requires more than energy. It requires synchronization, a shared clock, a control architecture. And then, as if responding to its own internal exchange, the swarm did something no one expected. It turned. Not gradually, not loosely. Every fragment executed the same maneuver at the same moment, shifting the entire stream by 0.04 degrees. That adjustment might sound small, but in orbital mechanics, it's enormous. That change was enough to convert a near pass into a guaranteed intercept. This was not a natural correction. Debris follows the orbit of its parent body. It doesn't recalculate. It doesn't adapt. It doesn't aim. This swarm did. Within minutes, emergency classifications were escalated. Systems designed for asteroid deflection scenarios were activated, not because of impact risk to the surface, but because of where the new trajectory pointed. The corrected path aligned precisely with Earth's high-latitude orbital zones, the regions where our satellites live, communication relays, navigation systems, weather monitoring, global positioning, the invisible infrastructure modern civilization depends on. The swarm wasn't heading toward oceans or empty space. It was threading itself into the most crowded and critical orbital real estate humanity has. At that point, the question was no longer whether something strange was happening. The question was intent. Natural objects don't choose targets. Natural objects don't communicate internally. Natural objects don't wake up, assess their position, and adjust course to intercept moving infrastructure. Whatever 3I Atlas released was no longer behaving like debris, it was behaving like a system, a distributed one, a coordinated one. And as new trajectory updates confirmed the intercept window tightening, attention turned to the one question no one could yet answer. If this swarm was deployed deliberately, then the object that released it was never just a comet. It was a carrier. By this point, the discussion inside scientific circles had moved past denial. The question was no longer whether the swarm was artificial. The question was what it was designed to do. Because intent, once established, changes everything. Let's establish what had already been confirmed beyond reasonable doubt. The object known as 3I Atlas released 50,000 fragments of near-identical size. Those fragments exhibited coherent oscillation at a fixed frequency. They demonstrated non-gravitational acceleration without recoil. They resisted solar gravity. They exchanged structured electromagnetic signals. And finally, they executed a synchronized course correction toward Earth's most strategically dense orbital region. None of these observations were speculative. Each was recorded by independent systems using different methodologies across multiple agencies. Taken together, they formed a picture that no existing natural model could accommodate. And yet, one detail stood out above all the others. The swarm wasn't aiming for Earth's surface. If this were an impact event, the trajectory would be different. The fragments would be converging toward a geographic location, or at least toward the planet's center of mass. Instead, their path threaded a narrow band, thousands of kilometers above the atmosphere, intersecting the orbital shell where satellites operate. That distinction mattered. A meteor storm, even a catastrophic one, is chaotic. It burns bright, causes damage, and ends. But what was approaching wasn't chaotic. It was surgical. The projected intercept zone overlapped with communication constellations, navigation arrays, and weather monitoring platforms, systems that don't just support modern life, but quietly enable it. Navigation, timing, data flow, global coordination. Remove those, and the consequences cascade. Inside tracking centers, simulations were run continuously. Each update tightened the probability envelope. Each hour, the swarm advanced another 150,000 kilometers closer. At a distance of roughly 1.2 million kilometers, It was already well inside the moon's orbit. That left very little time to react. And reaction itself was the next problem. Planetary defense systems are built to deal with large objects, deflect an asteroid, nudge a comet. Fragmentation is usually a last resort because debris multiplies risk. But this wasn't one object. It wasn't even a handful. It was 50,000 independent units moving as one. There was nothing to deflect. There was nothing to intercept cleanly. And worse still, no sign that the swarm was unaware of being observed. The internal signal traffic detected earlier hadn't stopped. If anything, it intensified. Bursts became more frequent. Patterns repeated faster. The system appeared to be updating itself in real time, reacting to its environment as it closed the distance. That raised a chilling possibility. If the swarm could sense us, then any overt defensive action could trigger a response. At that point, discussions shifted behind closed doors. Public feeds went dark, statements stopped, observatories continued to collect data, but release channels froze. This wasn't about preventing panic, it was about uncertainty. No one wanted to say the wrong thing while the situation evolved minute by minute. Because one final question remained unanswered. Why target orbital infrastructure instead of the planet itself? If the goal were destruction, there were simpler ways. If the goal were impact, aiming lower would make more sense. But disabling satellites doesn't destroy a civilization outright. It blinds it. It isolates it. It forces it to look inward, suddenly disconnected, which suggested something far more deliberate, preparation. And that leads us to the most unsettling realization of all. If this swarm is a probe system, then its arrival isn't the event, it's the test, and whatever happens next will tell us whether this is a warning or the opening move. If this swarm is a test, then the clock we're watching is not a countdown to impact, it's a countdown to evaluation. Every maneuver, every signal burst, every course correction looks less like chaos and more like observation. The system appears to be measuring something: response time, detection capability, reaction patterns. It's not rushing. It doesn't need to. From its current distance, the swarm has time. And that may be the most unsettling detail of all. The latest trajectory models show that the fragments will begin passing through Earth's orbital infrastructure window within the next 48 hours, not all at once, not as a single wave, but as a sustained passage, a drawn-out interaction that could last several hours. That duration matters because it allows the system to observe cause and effect, to see which satellites maneuver, which signals go silent, which systems adapt, and which don't. This isn't brute force. It's probing. Inside analysis rooms, one comparison keeps resurfacing, even if no one says it out loud. When humans explore unknown environments, we don't start with contact. We send scouts, instruments, sensors. We map before we engage. What's approaching Earth fits that logic disturbingly well. The fragments themselves are small. Individually, they don't pose an extinction-level threat, but that may be the point. Their size allows them to interact without catastrophic destruction, to interfere rather than obliterate, to observe consequences without triggering irreversible outcomes. And that suggests restraint, which raises the most difficult question of all. If restraint is present, then intent exists, and intent implies agency. At the moment, no transmission directed at Earth has been detected, no message, no greeting, no warning, just internal communication, constant and efficient, as the swarm closes in. It doesn't announce itself. It doesn't explain itself. It simply moves, adjusts, and watches. The final confirmation update places the swarm's intercept precisely where predicted: high-latitude orbital zones, communication belts, navigation networks. the silent scaffolding of modern civilization. If those systems go dark, even temporarily, the effects ripple outward. Flights reroute, financial systems desynchronize, emergency services lose coordination. It wouldn't be the end of the world,